how are you today? Today we are going to discuss on the stereochemistry of SN2 reactions. And we have already discussed the way SN2 reactions take place. So we will now discuss on the stereochemistry of SN2 reactions. And SN2 reactions require attack by the nucleophile on the backside of an electrophilic carbon atom that is bonded to the halogen. In this case, if we are to use if the substrate is an alkyl halide, but the substrate, as we said, can also be any other molecule which has the properties we've indicated in the earlier lectures. So for the alkyl halide, then that is the one we're going to give an example of how SN2 reactions take place. So the SN2 reaction requires attack by a nucleophile on the backside of an electrophilic carbon atom. Since the leaving group blocks attack from its side of the molecule, the only available part of the carbon's sp3 orbital is a small back lobe of sp3 orbital of the carbon which is bearing or is bonded to the halogen. Attack on this small back lobe is called backside attack. Backside attack turns the tetrahedron of the carbon atom inside out like an umbrella caught by wind. Remember, the carbon which is bearing the halogen is sp3 hybridized, and it has a tetrahedron structure or shape. So when there is a backside attack, it turns the tetrahedral of the carbon atom inside out like an umbrella caught by wind. You'll see this can be elaborated later. In the product, the nucleophile assumes a stereochemical position opposite the leaving group originally occupied. We call this result inversion of configuration. So in case of a chiral carbon atom, backside attack gives opposite configuration of the chiral carbon. The SN2 displacement is the most common example of a Walden inversion, a step in the reaction sequence where a chiral carbon atom undergoes inversion of configuration. So this is an example to elaborate that. So this is a sp3 hybridized carbon orbital, which will overlap with the p orbital of the halogens. And remember, the sp3 hybridized orbitals have the bigger lobe, which forms covalent bonds, and the other overlaps to form covalent bond. And then there's a smaller lobe which does not overlap with another orbital to form covalent bonds. So the attack of the nucleophile is from the backside or from the smaller lobe of the sp3 hybridized orbital. So this is a smaller lobe. And remember, this carbon is sp3 hybridized, so it is forming 4 covalent bonds. So one of the sp3 hybridized orbital is bonded or is overlapping with the p of the halogen. And then also you have the other 3 hybridized orbital in this particular molecule overlapping with the s of hydrogen. So, and these bonds are directed to the corners of a tetrahedron. Always remember that. So attack is on the back lobe of the sp3 hybridized orbital, which is bonded to the halogen. So in SN2 reaction, backside attack takes place on the small back lobe of the sp3 hybridized orbital that is bonded to the halogen. So this is an example of the mechanism of reaction for SN2. So this is a nucleophile, the hydroxyl. It's a strong nucleophile. It's attacking from the back lobe of this sp3 hybridized orbital that is bonded to the halogen, donates electrons, and goes through a transition state. That is a high energy state, and it's not really pentavalent, but it's tends to have almost like 5 covalent bonds. You can see this is trying to form the one to the new nucleophile, and the bond to the halogen is trying to break. And because carbon is tending to have 5 covalent bonds, it becomes very unstable, and this is a high energy state. And finally, The bond to the new nucleophile forms completely to the electrophilic carbon, and then the leaving group, that's the halogen, leaves with the 2 electrons of the covalent bond that bonded it to the electrophilic carbon as a halide. So it leaves with the 2 electrons. That's why it has a negative charge. So the most important here to note is that there is inversion of configuration, especially when you have a chiral carbon, the alkyl halide, the carbon which is bearing the halogen. If it's chiral, then it's easier to see. But even when it's not chiral, then there's always inversion of configuration. So in case this, for example, if this was like to show an umbrella, when there's a bond to this electrophilic carbon, there's like inversion of configuration. Of course, when a new bond is formed to this carbon, it means these other bonds to hydrogen have to move to the other. The configuration is inverted. So you like as it said here, it's like an umbrella caught by wind. You always can be inverted to the other side. So when a nucleophile forms a new bond to this electrophilic carbon, then finally you get these other the bonds to hydrogen to the other atoms now are inverted to the other side, and you get inversion of configuration. So this is another way this can be presented. If you have the hydroxyl group, then it attacks from the small lobe of the sp3 hybridized orbital of this carbon, which is bonded to the halogen. Then this is the transition state. So this bond is trying to form. Of course, it's overlapping with the smaller lobe. Then you can see now the size has increased because it's going to finally require, it will be increased so that it can effectively overlap with the oxygen orbital to form a covalent bond. Then this bond is trying to break at the transition state. Finally, this bond to halogen breaks and moves the 2 electrons. And you have the new bond to the hydroxyl group forms. Then this is the product, and you can see there's inversion of configuration. So initially the direction of the halogen was this way, but now the direction of the new nucleophile is on the opposite side, where because it has used the back lobe of the sp3 hybridized orbital of the carbon bearing the halogen to form the new bond. So there is always inversion of configuration. So again, this is another presentation where you have the hydroxyl group, and you can see clearly this alkyl halide is unhindered because it's a methyl halide. So this is the best for substrate for SN2 reactions when it's unhindered. This is the most unhindered. So it forms a new bond, then this bond breaks and the 2 electrons move with the bromide. In this case, there is an inversion of configuration. So the OH now is bonded here, and you can see clearly the other bonds to hydrogen are on the other side of the carbon atom. So the backside attack in SN2 reaction takes place through nucleophilic, this is a backside attack in the SN2 reaction. The SN2 reaction takes place through nucleophilic attack on the back lobe of the carbons, that is sp3 hybridized carbon. Then the backside attack inverts the carbon atoms, tetrahedron, like a strong wind inverts an umbrella. So that we've already talked. And here is inversion of configuration in SN2 reaction. This is a specific compound, which is chiral. This carbon, which is bearing the halogen, is chiral. It's attached to 4 different groups. So this is an S-configured alkyl halide, and it's known as 2-bromobutane, S2-bromobutane. So this is the normal transition state, which is high energy state, and it's pentavalent. And then finally the product forms, and the configuration now in this case is R. It's been inverted. So the product, which is the alcohol, when you're using a hydroxyl group as a nucleophile and you react with the substrate, that is the alkyl halide in this case, what you're trying to synthesize is an alcohol. So the alcohol will, the configuration for the alcohol will be the opposite of that of the alkyl halide. So the substrate was S configured, the configuration was S, but the alcohol, which is a product, will be R. So there is inversion of configuration from S to R. For SN2 reactions, there's always inversion of configurations. So this happens with all the SN2 reactions. There's always inversion of configuration from the reactant, that is the substrate, the alkyl halide, to the product, that is, in this case, the alcohol, but can be any other product depending on the nucleophile, which is used to donate electrons to the electrophilic carbon. So the product is always an inversion of configuration of the substrate. In some cases, inversion of configuration is readily apparent. For example, when cis-1-bromo-3-methyl cyclopentane undergoes SN2 displacement by hydroxide ion, inversion of configuration gives trans-3-methyl cyclopentanol. So if you start with the cis-1-bromo-3-methyl cyclopentane, then you have the hydroxide as a nucleophile, and this is a substrate. It's an alkyl halide, but a cyclic alkyl halide. So again, attack is from the backside of this carbon, which is bonded to the halogen of this particular sp3 hybridized orbital. So the back lobe of that particular hybrid orbital is the one where the oxygen donates electrons to form a new bond. This is a transition state, which is pentavalent. You can see this is trying to form, this is trying to break. Then there are three covalent bonds that are in existence, so it becomes pentavalent. Then finally, the bond to oxygen forms, and the bond to halogen breaks to form a halide, in this case bromide. Then of course, when you have the hydroxyl group, and remember this is a ring which has both two sides. So one side is the one which is having the bromide, and also you have this other substituent. There are two substituents. This is the cis isomer where the two substituents are on the same side of the ring. And if this bromide is on one side of the ring as the methyl, so it means the hydroxyl group will attack from the opposite side of the bromide, where the bromide atom is bonded, or even where the methyl is bonded. So the final product is where there will be a new bond on the opposite side of the leaving group. So the final product becomes trans-1-bromo-3-methyl cyclopentane. So there is inversion of configuration from the cis isomer to the trans isomer in the product. So the alkyl halide is a cis isomer, and because there is inversion of configuration in SN2 reaction, then the final product will become trans isomer. So the SN2 displacement is a good example of stereospecific reaction, one in which a particular stereoisomer reacts to give one specific stereoisomer of the product. Even in SN2 reaction, when there is no chiral center, it's possible to determine whether inversion of configuration has occurred. In these cases, we use kinetics and other evidences to help determine the reaction mechanism. So that is all about SN2 reactions. So next time we will discuss about first order nucleophilic substitution reactions known as SN1 reactions. Thank you.